Hello everyone and welcome to the 37th lecture of the course Advanced Structural Analysis. We have briefly seen the method of the matrix analysis using the computing programs in the last lecture for the plane frame system. We will continue with the similar discussion and we will try to see that how the assembly of the load vector as well as the global stiffness can be arranged, and then we will briefly look at the solution steps of the given system. So, as we were discussing in the last session that typically the member stiffness, which is typically known to us in the local member coordinates, is required to be converted into the global coordinates of the given system, and to do so we come up with a very simplistic transformation rule in which all the degrees of freedom with respect to the local member coordinates can be defined in terms of the degrees of freedom of the system in terms of the global coordinates. Now, this relationship is a general relationship for any vector, which means that the same idea will also hold for the forces and as well as for the displacements. So, with this idea we consider that all the forces of the given system which are defined in terms of say the individual local coordinates of the given system can also be expressed in terms of the amount of the forces in the global coordinates of the given system, and this can be simply done using the same transformation or the rotation matrix of the system, and this rotation matrix R we have defined as a 3 cross 3 system for the given problem. So, using this 3 cross 3 rotation matrix in the given problem, we are able to now make a transition between the member coordinate system contributions and the global system contributions. This is all being done at the individual element level only. So, we are able to identify the stiffness matrix for the element I in the global directions using the stiffness matrix which is known to us in the local member coordinates of the given system. Now, once we have this relationship available to us, we go with the identification of the global stiffness in the given system. Now, as we understand in the previous system, we come up with say the numbering of the given problem, say 1, 2, 3, 4, 5 and 6. So, if I locate this as a numbering, we understand that in the given system at each of the joint there will be 3 degrees of freedom which have been identified as 2 translations and 1 rotation in the given problem. So, I will just locate at few of the system and we can just see that at each and every system the degrees of freedom will be defined in the same manner of the given problem. So, totally as we have 6 number of joints in the given problem, we can identify that total 18 degrees of freedom in the given system will be there. So, the overall stiffness matrix will be now located with respect to these 18 degrees of freedom in the given system, which means that the global stiffness matrix will be having a size of 18 cross 18 in the given system, which means that 18 degrees of freedom which are located in the given problem, corresponding to each degrees of freedom we will identify the contributions of the stiffness matrix in the given system. But at the same time, while we have defined the individual elements stiffness matrix, say for any member I, we came up with the expression of S of Mi, and the size of this stiffness matrix for individual system is actually a 6 cross 6 matrix for the given problem. If we recall briefly, we have a 6 cross 6 stiffness matrix which was defined for the given system in the local coordinate. Then we defined the transformation rules, and through which we got again a stiffness matrix of the same size which is 6 cross 6. Now, it means that for any given member I, the user is knowing the contribution of the stiffness in the direction of these global degrees of freedom of the given system. Now, these degrees of freedom with respect to the joint J and K can be considered in the order of the standard global stiffness of the given system, which means that at the joint J, as I have 3 degrees of freedom assembled. So, I will now not go with the numbering as 1 to 6 in the given problem, but first I will just try to generalize it with respect to the idea of the joint J and K in the given problem, which means that as we have total n number of joints or n number of nodes in the given problem, at each of the node we have 3 degrees of freedom. So, that is where we are getting total 3 into n number of degrees of freedom in the system. So, for any jth joint of the given problem, we are supposed to get 3 degrees of freedom, and these degrees of freedom will be 3 into j, because that is the total number of degrees of freedom which we will end up with that particular joint, and the other 2 degrees of freedom will be 3j minus 1 and 3j minus 2 in the given problem. So, one can just cross check it. If I go to the joint number 3 of the given system, the individual degrees of freedom which I should get at that particular joint should be 3 into 3, which is the degree of freedom number 9, and then 9 minus 1 which is 8, and 9 minus 2, which is 7 in the given system. So, if I just number the systems, this is 1, 2 and 3, 4, 5 and 6, and this is 7, 8 and 9 in the given problem. So, this is a very standard expression which we realize that at any given joint we have the 3 degrees of freedom, which are say the joint J, 3j minus 2, 3j minus 1 and 3j in the given problem. So, I will just number them the degrees of freedom in the same manner. I say that this is 3 of j minus 2, this is 3 of j minus 1 and this is 3 of j in the given system. At the joint K, now one thing we must understand that while we were solving the beam problem, we had the numberings always in a continuous manner, though in this frame it also appears that the numberings are done in a continuous manner, but there may be situations where the numbers of the individual joints, say j and k, may not be the consecutive to each other. That we very rightly saw in the problem of the plane trusses as well. So, with this idea I just give the generalized numbering to the given system. So, for the joint K, I will have these degrees of freedom as 3k minus 2, 3k minus 1 and 3k in the given system. So, what we realize now that the stiffness matrix which we are going to get for the given system or the global system is a 18 cross 18 matrix, which are the total number of degrees of freedom in the given problem, and out of that the individual member I, which is located with the two of the joints j and k at the ends, is going to contribute to the degrees of freedom at the position of 3j minus 1, 3j minus 2, 3j minus 1, 3j and 3k minus 2, 3k minus 1 and 3k in the given system. So, what we will identify as that corresponding to the joint j and k of the member I, we will be locating these contributions in the overall stiffness matrix. As we say that total degrees of freedom in the system are n, so the total size of the stiffness matrix will be 3n cross 3n. Now, I am going to the specific values in the global assembly in the position of row number. So, I will just number these systems as 3j minus 2, 3j minus 1 and 3j in the given problem. Similarly, these with respect to the joint K can be written as 3k minus 2, 3k minus 1 and 3k in the given system. So, with this idea, I consider now that the given system with respect to the joint J will come out as 3j minus 2, 3j minus 1 and 3j as the 3 rows. Similarly, these 3 columns will also be associated with it. So, 3j minus 2, 3j minus 1 and 3j of the given system. The remaining 3 rows of the given system will be associated with the joint K of the given system. So, this will be appearing as 3k minus 2, 3 of k minus 1 and 3 of k in the given system. Similarly, the remaining 3 columns of the given system will also be associated with the corresponding joint K of the given system. So, this will be 3k minus 2, 3k minus 1 and 3k in the given problem. So, now what we realize is that individual member I is going to contribute to a stiffness matrix which is of the size 6 cross 6, and that is going to remain same across all the members. Each of the member will have its own stiffness matrix which will be of the size 6 cross 6, but where to place that matrix in the global assembly? So, we got the answer that in the global assembly which is of the size 3n cross 3n, I will go to the row numbers 3j minus 2, 3j minus 1 and 3j, as well as the row number 3k minus 1, 3k minus 2 and 3k of the given system, and now I will place the components of the stiffness matrix of the system in this manner at these positions. So, these are the subcomponents of the stiffness matrix, which means that when we define the stiffness matrix for the given problem or for the given joint given member I, we located it in the order of these 3 degrees of freedom at the node j and 3 degrees of freedom at the node k of the given system, which means that this was delta 1, delta 2, delta 3, delta 4, 5 and 6 of the given system, where 1 to 3 was located with respect to the position of the joint j and 4 to 6 was located with respect to the position of the joint k in the given system. So, from the stiffness matrix which we defined for the individual member I of the given system, we pick this first 3 cross 3 system, call it as say S1, and we place this in this position which is corresponding to, which is corresponding to the first 3 degrees of freedom of the given system. Similarly, corresponding to the second component which is over here, we realize that these are the contribution with respect to the same rows of delta 1, delta 2 and delta 3, but these are getting multiplied with the columns of delta 4, delta 5 and delta 6 of the given system, which means that in a typical stiffness matrix, we understand that the rows are the contributions with respect to the equilibrium equations of the given system. So, the first 3 rows are the equilibrium equations with respect to the joint J and its 3 degrees of freedom, whereas the individual columns are the contributions of the degrees of freedom with respect to the all component of the degrees of freedom in the system. So, the first 3 rows are the contribution with respect to the same 3 degrees of freedom of the system, whereas the next 3 columns of the system, they are the contributions in the equilibrium equation corresponding to the joint J with respect to the degrees of freedom of the joint K of the system. Okay. So, means again I will repeat this part, that individually in the stiffness matrix which is defined at a for any member I, the individual rows, they typically describe the equilibrium equations of the system. So, if I say that the first row of the system, so the first row is defining the equilibrium equation with respect to the first degree of freedom in the given system. So, if I say that this is the first degree of freedom, so this is the equilibrium equation corresponding to that. Now, this equilibrium equation will be defined in terms of all the possible degrees of freedom of the given system. So, it will have the contribution of the degree of freedom delta 1, delta 2, delta 3, delta 4, 5 and 6 of the given system. So, as a next point of the realization, we understand that corresponding to the equilibrium with respect to the delta 1 position, we are going to get the contributions in terms of the delta 1, delta 2, delta 3, delta 4, delta 5 and delta 6, and these are the individual stiffness contributions of the given system. So, in the columns we have arranged these values, whereas in the individual rows we are writing these equilibrium equations of the given system. So, from this submatrix we will just pick up these values, say S1 to S4 of the given system, and now what we do, we place them very judiciously in the positions where they belong in the given system. So, we first said that these 3 joints, so of course these must be defining the equilibrium equations with respect to the respective joint J and its 3 degrees of freedom, and now the individual columns which will come in this particular part, of course the other columns will also be having their values. At this point we are only associating ourselves with the member I, so that is where I am assembling only the contribution of the member I in the given system. But what does it mean? That each of these columns in the 3j minus 2 row is the contribution of the respective degrees of freedom of the global system. Out of that, the contribution with respect to the member I, which is having these 3 degrees of freedom at the joint J and these 3 degrees of freedom at the joint K, labeled as 3j minus 2, 3j minus 1 and 3j, and 3k minus 2, 3k minus 1 and 3k in the system, have been identified as a part of S1 and S2 in the given system. So, what I will do now, I will place this S1 which is the 3 cross 3 matrix in this position, S2 I will be placing over here, S3 will be placed at this position and S4 will be placed at this position of the given system, right. So, by placing it, it is a very simplistic system, one can easily understand it, but we must also realize that what is the meaning behind it. It typically means that individual rows which are contributing to the equilibrium of the system and the individual columns, they are contributing to the coefficients with respect to the degrees of freedom of the given system. So, the same contribution we are defining in the global system as well. So, this is the contribution of the member I stiffness which has been added in the given problem. We will keep on repeating this for each of the member in a loop, and we will do it in such a manner that wherever we get the overlap, say if at this point again a new value is going to occur, so the previous value will be added on top of it. This way we will not be losing out the contributions of the remaining members. Okay. So, once we are able to do this kind of assembly in the given problem, we get the overall stiffness matrix of the given system. In the same manner, we also do the assembly for the load vector. We realize that in the given system, as there are 6 number of joints, I will just label them again. So, corresponding to these 6 number of joints in the given problem, we have total 18 degrees of freedom in the system. So, that is what we got, or in the system which is having n number of joints, we can simply say that we have total 3n number of degrees of freedom in the given system. That means, now I am going to locate the joint load vector which is of the size of 3n cross 1, in which individual components refer to the amount of the joint load contribution in the direction of these degrees of freedom which are defined at each of the joint of the given problem. So, at each of the joint we have 3 degrees of freedom. So, having n number of joints, we have total 3n degrees of freedom in the system, and at each of the joint we are trying to define that what is the contribution of the load of the given system. Now, as we have done earlier the calculation, to calculate the load contribution, we said that if you bring any of the member I of the given system, so ith member is connected to two of the joints, say the joint J and the joint K. We already got to know that corresponding to any kind of a load, say if it is having a uniformly distributed load on top of it, we can calculate the fixed end reactions of the given system. Say I can easily calculate these reactions of the given system. Also the horizontal components we are defining, so we will call that this value is 0, this value is WL by 2 and this value is WL square upon 12 in the given problem. Once knowing these values, what one can easily do, we can identify them as a fixed end forces of the given member I in the direction of the individual member coordinates, and this is what we define as a individual vector of the given system. Now, we can convert this vector into the global coordinates of the given system. So, we did that for the member I, the fixed ended forces can be calculated in the direction of the global degrees of freedom by doing a simple transformation matrix representation, and this is what we get for the given system. Now, once we have these values which are located as the fixed ended contributions at the end J and K of the system with respect to the member I, but these are located in the directions of the global degrees of freedom, which means that now these contributions have been located at the two ends. If I just define the, say, both the ends being restraint and this being the uniformly distributed load. So, these reactions or the A of Mi with respect to the fixed end part are the contributions in the global directions of the given system. Now, these contributions, once they have been identified, could be just reversed in their direction, which means that I will just opposite the sign of these values and they will become the equivalent joint loads of the given problem. So, we call it as that this is for any of the member I, the respective equivalent joint load in the given problem. So, once we have this equivalent joint load in the problem, what we also realize that these equivalent joint loads are also going to get in the directions of the 3 degrees of freedom with respect to the joint K, J, and 3 degrees of freedom with respect to the joint K of the given system. So, I will again label them in the similar manner and they will come out as 3j minus 2, 3j minus 1 and 3j in the given problem, and with respect to the joint K, 3k minus 2, 3k minus 1 and 3k in the given system, which means that the 6 values of the A of I which I am getting in the system So, I am just defining these values as per the numbering 1 to 3 in the system. So, 1, 2, 3 refer to the position with respect to this is 1, this is 2 and this is 3, this is 4, this is 5 and this is 6. So, the directions the way I have taken here are just according to the standard problem which I considered. So, they will be accordingly given the values of positive and negative, but the understanding is that if I get the values of the system and I locate them in this order, so these 6 values which we have located in the system, the first 3 will be going to the corresponding position of 3j minus 2, 3j minus 1 and 3j in the given system, which means that these 3 values will be located to these positions, whereas the remaining 3 values which are 4, 5 and 6 will be going to the position with respect to the joint K, and these are 3k minus 2, 3k minus 1 and 3k in the given system. So, as I said, we will again repeat the similar process for all the members, and while doing it we will ensure that the previously existing values are added on top of the new appearing values of the given system, and this way we will be able to assemble the overall load contributions of the given system. So, the overall load contribution which we get of the given system, the equivalent joint load, is the submission with respect to all the degrees of freedom of the given problem, and we contribute it with respect to the individual contributions defined by each of the member. Once we are done with this, we define that the total contribution of the load, which is the A of S, is equal to A of J plus A of E in the given problem, which means that the loads which are directly active at the joints, they have already contributed their values. The loads which are considered with respect to the equivalent joint load, they have been also evaluated with respect to the identification of the individual member contributions, and finally this is the total value of the load vector which we get for the overall problem. Having these values in the system, now we can go ahead with the identification of the support conditions and the solution of the given problem. To do so, what we realize that the S of S has been identified of the size 3n cross 3n. The A of S has also been defined of a size of 3n cross 1, and if we realize that the delta S, which is the displacements of the system, will also be known with the size of 3n cross 1 in the given problem. But what we realize that these all degrees of freedom of the system have been arranged in the order of the standard number of the nodes which we have defined in the problem. So, the S of S is going in the position of the degrees of freedom 1 to 18, A of S is also going in the same order 1 to 18 of the given problem, and delta S is also going in the position of 1 to 18 in the given problem. So, now solving this problem is not directly possible, because what we realize that if I write this expression, I write it as that A of S is equal to S of S into delta S. So, we realize that in the delta S, in the overall structural displacement point, some of the displacements are known to us which are corresponding to the restraint condition, whereas some of the displacements are unknown to us. In the same manner, in the AS vector also, some of the components have been calculated and these are the final values, whereas some of the components which have been calculated will also be getting the contribution of the unknown reactions in the system, which is not known till now. So, we realize that in the A of S as well as in the delta S, there are some of the values which are known and unknown to the user. So, what we do further, we try to bifurcate the given system into two subparts, one with respect to all the degrees of freedom which are free in the given problem, and second with respect to all the degrees of freedom which are restrained in the given problem. So, this is typically called as the arrangement of the given system. So, we realize that if I just do it for this given problem, initially we have total 18 degrees of freedom as we define. So, I will just locate all these values, and now we realize that corresponding to these degrees of freedom which are totally 1 to 18 in the given problem, degrees of freedom at the joint 1 which are 1, 2 and 3, these are the 3 degrees of freedom which are restrained, which are not allowed to move in the given problem. At the same time, other all degrees of freedom with respect to the joint 2, 3, 4, they are free, they can be allowed. When I come to the joint 6, I have these two translations which are again not allowed to take place at this point. So, I say that 16 and 17. So, at the joint 6 means I have 3 degrees of freedom. Now, I can again go back to the idea like same way, that it is 3j minus, or if I say any normal joint 10, 3n minus 2, 3n minus 1 and 3n. So, using this idea, I get that there are 3 degrees of freedom which are 16, 17 and 18 in the given problem. So, 16 and 17 are the two which are restrained in the given system. Similarly, at the joint 5, when I come, I define here that there are 3 degrees of freedom over here. So, the realization is n value is now 5. So, it will come out as 15 minus 2, which is 13, 14 and 15 in the given problem. So, in the joint 5, I realize that there are again 2 degrees of freedom, 1 degree of freedom which is restrained in the given problem, which is the degree of freedom corresponding to the vertical translation, or 14 in the given problem. So, we finally locate that 1, 2, 3, 16, 17 and 14. These are the degrees of freedom which are restrained in the given problem. So, I locate them as one set of vector components, say 1, 2, 3, 14, 16 and 17, and remaining all the degrees of freedom which are defined in the given problem, which are other than these degrees of freedom, they are free or allowed to take place in the given problem. So, now the intention is that the S of S as a matrix which was earlier arranged in the order of 1 to 18 in the given problem, with all the rows as well as all the columns of the given system. Now, we need to change the arrangement of that matrix, and we need to bring the arrangement such that I need to fix the order of the degrees of freedom which are corresponding to the free components and the degrees of freedom which are corresponding to the restrained components of the given system. So, with this idea, I have now the restrained degrees of freedom, which are 1, 4, 3, 14, 16 and 17, whereas the free degrees of freedom will be 4, 5, 6, 7, 8, 9, 10, 11. So, I will just write it on the other side so that all numbers I can arrange. So, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, then 18. So, these are all the degrees of freedom which are free, these are all the degrees of freedom which are restrained in the given problem. So, as a next step, what we do, the individual degrees of freedom which were arranged in the order of 1 to 18, we will just change their standard arrangement by keeping first the degrees of freedom which are free, which means that now free degrees of freedom which have been just defined in the previous slide as 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15 and 18 will be written first, which means that I will change the order of all the rows in the system such that the row number 4, 5, 6, 7, 8, 9, 10, 11, 12, then I think 13, 15 and 18. So, these rows will be written first in the given system. So, this is like you switch the rows, you change the row number 4 from here and move it to the top of the given system. So, this becomes the new row 4 of the given system, which is written at the position 1. Similarly, I also change the remaining rows of the system, which is the 1, 2, 3, 14, 16 and 17, right. But by only changing rows I cannot complete it. So, what I also need to do as a next process, I need to change the columns of the given system. So, columns will also be arranged in the same manner, which means that I will switch the column number 4 and bring it to the first. I will then bring the column number 5, column number 6, 7, 8, 9, 10, 11, 12, then 13 and then 15 in the given part. Then finally, up to 18. So, these are all the columns which are related to the restraint, the free degrees of freedom of the given system, and then the column numbers which are corresponding to the free degrees of freedom of the given system. So, we get the system in this order. So, the initial stiffness matrix, which was 18 cross 18, we will change all the rows of the system in this order, and we will also change the columns of the system in this order, and this way we get a new standard stiffness matrix of the given system, which is a rearranged stiffness matrix. As we are doing this procedure with the stiffness matrix, we must recall that the same thing also need to be done with the force vector. So, A of S, which is defined with the 18 number of components in the given system and which is having the size of 18 cross 1, will first be written with the number of positions with respect to these degrees of freedom, which are the degrees of freedom which are corresponding to the free degrees of freedom. Then we will write the component of the forces with respect to the degrees of freedom which are restrained in the given problem. And this will also define now that A of S will be broken down into two parts, one corresponding to the free and second corresponding to the restrained degrees of freedom of the given problem. The moment we do it, we realize that this contribution, which has been of course evaluated at the beginning with respect to the restrained components, is not the actual final value. So, we only say that this is the contribution due to the loading in the given part. Okay. So, this modification we keep here, that A of RL is the contribution of the overall load vector based upon the external loads which are active in the direction of the actual restrained degrees of freedom. So, these are the contribution which will not be otherwise evaluated in the system, and we will try to take contribution of that in the last step. So, now as a part of the process, we have this equation to be solved. We know that stiffness matrix once arranged, we know all the values of it. Delta of F, which are the degrees of freedom corresponding to the free degrees of freedom, we do not know these values, these are unknown to us. Delta of R, degrees of freedom which are restrained in the given problem, we know all these values because either they will be 0 or they will be given some finite values of the given system. A of F, which are corresponding to the force, which are the forces corresponding to the degrees of freedom which are free. If we have already evaluated A of S and arranged it in this order, we know the A of F value of the given system also. So, this is a known value to us, and A of R, which is the final value, is not known to us. We do not know the reactions of the system exactly. So, that is why these values remain unknown to us. So, now what we do, we break this system of the equation. We say that A of F is equal to S of FF delta F plus S of Fr into delta R. In this equation we realize that this value is known to us, stiffness parameters are all known to us, delta of F is an unknown parameter, whereas delta of R is a known parameter to the given system. So, I can now do a simplistic rearrangement and get the value of delta F as S of Ff inverse A of F minus S of Fr delta R. So, using this idea, now I am able to calculate the individual degrees of freedom which are free to take place in the given system. As a next step, we also evaluate, once we have known the value of delta F, we go to the second equation and we say that A of R is equal to S of Rf delta F plus S of Rr delta R in the given problem. As delta R is already known to us, delta F has been evaluated already in this step. So, we can now calculate the value of A of R in the given system also. But as we already said that A of R while evaluated in the system is only getting the contributions with respect to the displacement parameters of the given system which have been evaluated over here. Whereas the loads which are directly active in the direction of these restrained degrees of freedom, say at this particular degree of freedom, if there was a contribution of the load which was already coming, that has not been added in the analysis at any point, because the respective values with respect to those degrees of freedom like 1, 2, 3, 14, 16 and 17 have not been added anywhere in the system. So, what we do, those individual load contributions which have been evaluated in the direction of these restrained degrees of freedom, we need to add the contribution of the reaction due to that, and as these are the external loads active on the given system, the reaction will be opposite to that, and that is why we say that the A of R, the final value or the ultimate value of the reactions at the system will be A of R, which has been already evaluated over here, plus the minus of A of RL. So, A of RL is the contribution with respect to all these degrees of freedom which are restrained in the given problem. These are the contribution due to the external load. So, we will just reverse these direction and they will become the reaction components of the given system. So, with this idea we get the values of the reaction components of the given system. So, this has been defined over here, that we get the value of A of RL, which is the contribution of the reaction which is the contribution of the reaction due to the external load in the given system. Now, once we are done with this part of the procedure, we now look for the calculation of the member forces. We realize that member forces can be calculated by the simplistic procedure that the for each of the member we know that what is the stiffness matrix in the global coordinates. So, this value is in the global coordinates into the delta of I. So, for each of the member we can now pick the values of the delta I which are evaluated for the given problem. So, the delta F which we have obtained in the given problem, once that value is known to us, delta R which is also defined already at the beginning, which means all the restraint values. So, we arrange all them in the order of the standard degrees of freedom in the given system, and that becomes the delta. Out of those we will pick specifically those values which are corresponding to the delta of I, which is the ith member of the given system. So, if I say that ith member is having 2 of the joint j and k in the given problem, so I can now locate out of the delta the individual values with respect to 3j minus 2, 3j minus 1 and 3j, and 3k minus 2, 3k minus 1 and 3k. These respective positions I will pick the values and they will be the delta I for the given system. Multiplying these two will give me the amount of the member forces in the given system. But as we also recall that the equivalent joint load method gives us not the direct force in the member, but we also need to add the contribution due to the fixed end forces of the system. So, we will again calculate that what were the reactions due to the fixed end forces of the given member I, which has been already evaluated, and we add that contribution to get the net moment net force in the given member. So, with this part we are able to complete the overall analysis of the plane frame members. We will briefly see in the next session a simple problem in which we can implement the same concept. So, approach which we have defined here is very systematic and it is in the same manner as we defined it for the beam and the plane truss members. Much of the problems which we typically look for, those will be the large scale systems. So, solving them using the manual method may not be possible. So, what is expected that we also use it with the computing system. We take the matrix multiplication as well as the other related terms for evaluation in the computer program, and then we can evaluate the response of the given system. With this we stop over here. Thank you everyone.